So welcome back. Now we continue with the second part of the discussion where we will dive deeper on the topic. And this discussion will be moderated by Mr. Ivan Grove. So I welcome Mr. Ivan here to set up the scene and also introduce the panelist and himself.
Thanks a lot, Aurora. Thank you very much. And good morning, ladies and gentlemen. It's still a good morning, isn't it? My name is Eivind Grøv, and I'm working as a chief scientist at SINTEF in Trondheim, Norway. SINTEF is actually a research institute, and we are very closely connected to the university in Trondheim, and therefore a lot of people have dual positions, being a professor at the university and working part-time with SINTEF, or the other way around. So I have also been a professor at the university as an adjunct professorship. It's a great pleasure to be here at Hagebakk again, and for this particular type of projects that we are about to discuss. I will give a small presentation afterwards, which may be a little provocative, but I think that is always good when there is a panel discussions we are here to have. But before I start, I would like to ask the panelists to introduce themselves, say a few words, what they are doing and what their particular kind of interest is with respect to the topic that we are discussing here today. So please, we can start with you.
So Pascal Brian, you know already me, and unfortunately for you, I think you have to see me for the three different topics. So I am a civil engineer specialized in tunneling works. I have been working more than 30 years ago as a contractor, doing 15 years excavating and completing tunnels for road, for trains, for hydropower, for sewage, for different fuels. And then I have been joining Geostock. You have already seen Geostock field of competence for the engineering and construction follow-up. And I have been working 10 years on one project in Singapore for the crude oil storage, and very recently 5 years in UAE for also crude oil storage, a very big one. That's it. And now I'm working on among Geostock, I'm working on the H2 issues for the storage in mine rock caverns.
Thank you. My name is Anmol Bedi. I'm a tunnelling and geotechnical engineer, and I'm managing director of a small consultancy, Bedi Consulting. We are solely tunnelling and geotechnical engineers, so I don't have much of an energy background. But we've been working for the past year and a half with a company called Fortescue Future Industries, which is now rebranded as Fortescue, who are looking to generate hydrogen and store hydrogen underground as part of their portfolio to decarbonise their mining operations in Australia. So what I'll present today is a collaboration with them. So I've got 22 years experience in tunnelling and geotechnics, primarily mining in Australia, but I've been in London, UK for the last 17 years. I just finished my PhD in 2013 at Imperial College in rock mechanics. And yeah, that's where I am at.
I'm Matthias Reinhold. I'm originally German civil engineer and materials engineer. Started my career off in Germany as a materials researcher and later on teacher and trainer in the field. And then actually I worked in Hagebakk for 3 years, believe it or not, and then joined Normet 10.5 years ago in different positions in UK first, and was involved also in Crossrail project and all those prestige projects, and then moved to Australia. I've been technical manager there for a while, and then I was promoted into a global position, and now I'm looking after the chemical part of our business. Normet is a supply company in underground construction. We supply machinery and we supply chemicals, and I'm on the chemical part of the business.
Thank you.
Christian Jensen. I'm a senior advisor at a startup company called Horisont Energy in Norway. We are doing a CCS project, and we are also doing a blue hydrogen project. My background is mechanical engineering, and my only tunneling activities as 2 summer holidays as an mechanic, so doing shafts in hydroelectric power plants. I've been working, I started my career into a green hydrogen plant in Glomfjord, Norway, where we were producing hydrogen from stranded electricity. We had a power plant with 25 cycle power, and which were not possible to send out on the grid. Henceforth, we were producing hydrogen from that one, producing 65 tons of hydrogen per day in that plant, which later on was converted to ammonia. Most of my life, I've been working with hydrogen, ammonia, fertilizers, but I've also been working quite a long time within the oil and gas industry of Norway. And as I said, right now we are working in a ammonia project, blue ammonia project, where we are going to produce blue ammonia and store ammonia in a rock cavern storage.
Thank you, Christian. Then I do it slightly different from the way that Anatolia did. I will give the presenters their turn. They will present each and every one of them, 10 minutes or something like that, in a row without being interrupted. And then we collect all the questions and the discussions at the end of the presentations. But I will start. A couple of months ago, I was hosting a group of people coming from China, actually, and we were discussing on the whiteboard, where are we now with respect to storage of different types of products in underground caverns. Norway has a lot of hydroelectric power schemes, and what we have been aiming at always is try to make these pressurized tunnels unlined. So today we have pressure tunnels with a pressure of 1,046 meters in unlined tunnels. And then we started to develop this thing that you see on the screen here now. It's handwritten, so it's not looking very nice, but it's just the way we were thinking at that point in time. So the next we have been doing is actually to use the same technology, the same thinking, the same philosophy with respect to unlined caverns for storage of LPG. And we have quite a few of those unlined caverns, and we have, I think we have down to minus 42 degrees as the most at 1 atmospheric pressure. We also do have ammonia, and I think Christian will talk more about that. And at the moment, that is actually where we have the state of the art. We haven't got any further than that. We have been looking at storage of CO2, Christian and myself together in a project where CO2 stored in a unlined rock cavern was the topic we discussed at that time. We had scenarios with down to 55 degrees minus, I think it was, and 7-8 bars, and the other one 15 bars and 35 degrees below zero. But that has not yet been materialized. So that's why I put that red thing in the middle. This is where we have state of the art with respect to unlined tunnels and caverns. If we would like to go any further, and you can see also hydrogen, H2, is somewhere above CO2 there, up on top of the ladder. And we call this the ladder of complexity. It doesn't mean that unlined head-race tunnels is not very complex. By far, it is not. But it's a matter of giving a scale to this, what we are doing and what we are dealing with. So that's where the frontier of competence is at the moment. And we, as I said, we are looking at always unlined. And you may ask, why do we do that? This is just a schematic way to show how we are actually working with different types of methods to control potential gas leakage. We have permeability control, and we have hydrodynamic containment, two different aspects. As you can see, the lining possibility is a method with respect to permeability control. But you also see that grouting is one way to reduce the permeability. Another is freezing. So lining, grouting, and freezing. In a saturated rock mass, if we insert a product which is frozen, there is a freezing taking place. So there will be a cap of frozen water in the rock mass following the freezing of or injection of the product. When it comes to hydrodynamic containment, water curtain is the main measure towards that containment. We do not trust the natural groundwater because in many cases we will try to put these as high as possible, as close as possible to the surface to reduce the length of tunnels that are actually leading to the caverns. That is to minimize cost. So water curtain is one of the major issues that we are dealing with together with grouting. These two things we have to do ourselves as a measure to have hydrodynamic containment and permeability containment or permeability control. Water is, of course, both a troublesome thing as well as is something that is actually a saver for us. As I said, water in the surroundings of the cavern will freeze when we are injecting the product, and that will make a cap around the cavern. But it will continue to grow, and we have seen that from numerical models reaching something like 60 meters away from the cavern periphery after 22 years. That is with minus 55 degrees and 7 bar pressure. 60 meters, it's just growing and growing and growing. And at 60 meters, you can see on the graph there, it's sort of balancing off. Goes to a kind of steady state. The trouble with water is that if there is a leakage into a cavern where there is a frozen product located or stored, this water will start to, what do you call that in English? That will start to steal, it will form ice, and it will start to steal the volume in the caverns themselves. And I think that we have had maybe 1 or 2 occasions in Scandinavia where we actually have had to abandon the cavern because we lost the product storage volume. And that's not good. But in principle, water is always a good thing to have, groundwater plus the hydrodynamic confinement with the barriers that we are making with the water curtain. This graph on the right-hand side tells us how has unlined tunnels been developed in the hydroelectric power schemes in Norway. We can go back to the 1950, and we had something like a couple of 100 meters with water pressure in unlined caverns, in unlined tunnels. Today, as you can see on the far right-hand side, upper right-hand side, we have 1,046 meters of water pressure in an unlined headrest tunnel. That is a project that was done back in 2005, 6 or something like that. They have also a kind of a system which is called water or air cushion search chambers where we are using water curtains actively. You can see the picture on the lower right-hand side, which is an air cushion search chamber at a project which was completed back in the middle of the 80s. And you can see that the air cushion chamber itself is formed like a donut, and there are water curtain holes which are covering the entire area of that air cushion chamber. And the pressure in these holes for the water curtain is something like half a megapascal above the water pressure in that air cushion chamber. So there's an air-filled area or air-filled volume which is pressurized, and then you have the water curtain on top of that, which is then there to take fluctuations in the pressure when the hydropower tunnel system is in operation. This is just some statistics. You can see that with respect to hydropower projects, the use of air cushion chambers have totally reached, I think, 13 different projects with the highest pressure of 7.8 megapascal in the air cushion chamber itself. On the right-hand side, you see a list of different projects where we have stored LPG, different types of LPG. And as it says, I don't think that any of these LPGs have ever been suffering from leakage unless one which had a leakage of water coming into the cavern itself, and that was later on abandoned. Well, just one thing, which I forgot to say. The minimum stress component, sigma 3, is a major stakeholder in the possibility of actually being able to make this kind of facilities. We have to know the minimum stress component. That is the natural resistance towards product trying to escape from the cavern or from the headrest tunnel. Sigma 3 needs to be measured. We need to have a sigma 3 which has a certain level and factor safety with respect to the storage pressure that we are actually using. An article prepared back in the 80s demonstrated at that time very clearly the benefits from going underground in unlined caverns compared to surface steel tanks. And you can see when the storage volume starts to increase to a decent level, lined tanks at the surface is no longer an option economically. So when it comes to hydrogen, as has been said earlier, and which is probably going to be said a number of times today, this is something which is in the very beginning of development. I'm not saying that we can do unlined caverns for storage of hydrogen by far, but I think that to some extent we also have to, open up the room for discussions and being a little bit forward-leaning. And that's why I presented this in the way that I've done. I've added the phase diagrams for ammonia on top and hydrogen in the bottom there, so that you see yourself the differences of these two products. Of course, if we are going to store hydrogen in underground caverns, we have to go down to a temperature of 250 degrees minus or something like that, and maybe 200 bars pressure. So it's a totally different ball game, absolutely. But from a cost and time concept or point of view, unlined is definitely favorable. And there is, of course, a whole lot of other issues that need to be solved. But that's why we are here, to start the discussions and start to look at the possibilities. So, that was my introduction. And then I leave to the speakers.
Okay, yeah, thank you very much for having me here. So as I said, we're a consulting company. Betty Consulting is tunneling and underground structures. But we've been working with Fortescue Future Industries, now Fortescue, and looking at developing underground storage possibilities for hydrogen. My talk is just going to, just quickly, because Fortescue couldn't be here, unfortunately, it's a long way from Australia, look at just summarise what Fortescue's aims are. Who needs H2, a quick touch on the types of storage, the issues with each of those, and what we've been doing with Fortescue to work on line tunnel storage and what issues these might help resolve. And as Ivan said earlier on, the technical challenges are immense, so a quick touch on the technical challenges to the solution. And the technical qualification process as well, which is really important. You know, it's a new industry and an emerging technology, and there are no standards that we're aware of for underground storage of hydrogen. So the technological qualification process is important, and that's, you know, we're at one of the best underground research facilities in the world. So you know, it's potentially a good space to start talking about how the technological qualification can be started. So this is what Fortescue do. They're a mining company started in Australia. They have iron ore operations, but they've now expanded into looking at green energy projects. So their targets here are to essentially decarbonise their mining operations, so reduce the CO2 emissions by 90%, and enable a reduction in emissions from steel making from 21 levels by 7.5%, and enable reductions in emission intensity levels for shipping their iron as well. They currently have 2 pilot projects in Australia, which have commenced. The first one is Christmas Creek Green Iron Pilot. So that's just started at 50 million capital expenditure, looking at decarbonising the production of iron ore. And also this project in Gladstone in Queensland called PEM50, which is looking at producing hydrogen at the minute, and we've been working with them and looking at ways to store hydrogen from that facility. So who needs H2 storage? You guys all probably know this, but just a quick recap of where the market is for HS2 storage, or the need is for HS2 storage. Someone touched on ammonia. So, you know, energy from intermittent sources, and the need for hydrogen storage is really based on the intermittency of the storage. Producing green hydrogen from electrolyzers and storing that as required prior to compressing and producing ammonia. So another industry application is the production of green steel. So again, using green energy from intermittent energy sources and electrolyzers, and storing that hydrogen when needed for the steel production process. And then obviously public use. You know, if we can get it into the public supply chain, again, there's a need for storage in times where energy is not being produced and then sent out to the grid as possible. So types of storages and issues currently. So one of the sort of everyone seems to be using steel tanks on the surface for short-term daily storage. Now, someone mentioned earlier on about the cost implication of these, and I think Ivan just put up a slide earlier on about 0 to about 100 tonnes of storage before they become financially cost ineffective. And then we have the large-scale end of the spectrum, where we have salt caverns and depleted oil fields, etc. Very useful for storing very, very large volumes of hydrogen. The issues with these, in Australia they call these steel bullets, or hydrogen bullets, the high capex cost of material, and obviously the safety issues with keeping these above ground at high pressure, and they require a large surface footprint as well. The issues with the geological storage, like salt caverns and depleted oil fields, is that you need them. So the storage needs to be in a place where they exist. So they can be constrained location-wise and geologically constrained, and they're not easily scalable. So it depends on the size of the cavern that's available to how cost-effective that storage is. So there's a gap potentially in the market here. Intermittent daily storage of somewhere between 100 and 600 tonnes. unfortunately, I haven't referenced this figure. This is not my figure. It's from Johansson et al. So this is the concept that they've developed of line rock caverns and published in Scullin. And we've used a lot of the work that they've done. And Ivan mentioned earlier on about unlined rock caverns. I'm not so brave to do that, but we're using the concepts of unlined rock caverns and lined rock caverns to see whether we can get rid of the essentially it's the geological constraint. Can the solution be engineered over a range of geologies and a range of scales to suit that gap? So what we're working on developing underground storage complexes for a feasible range of geological conditions, so not always confined to hard rock masses. And the concept utilises the mass of the confining rock, and some of the concepts that Ivan mentioned, sigma 3, etc., knowing the in situ stresses and the rock stiffness and strength, to see if we can extend the range of geologies over which hydrogen can be stored underground at viable depths. And we've worked for about 1.5 years with Fortescue and developed a reference design and a concept. So we're at a stage that we need to verify the performance of that. It's just theoretical at the moment in terms of analysis has been done numerically and analytically, and concepts developed together with FFI. And we've been looking at other materials as well, so not just steel and concrete, but we've been working with the likes of Normet, et cetera, looking at whether polymers, et cetera, can be used to contain hydrogen. And this is just a summary then of how Fortescue are looking to apply the work that we've been doing. So some of Fortescue's projects could benefit from underground storage. They're interested in the line tunnel storage technology, which is now the subject of a pending patent application. And again, because they're looking at using green hydrogen, which requires intermittent power of different scales and cost-effective solutions, they're looking at continuing development of this technology. So as a background, what are the technical challenges? This is just a slide summarising a general concept of all sort of underground containment solutions. So I've broken it down into 7 real components or parts of the system that have technological challenges that need to be solved. So obviously we need to contain the gas. So the internal gas containment system needs a lot of work and assurance. And then a drainage layer and a leak detection layer behind it. So if we have external water pressures, we need to make sure that we are somehow managing external groundwater pressures in a situation where we empty the pressure vessel, as well as internal pressures. Then the structural units of concrete or reinforced concrete, etc., and an annulus gap to give that sufficient contact with the surrounding ground. And then we have a zone of plastic or fractured rock, so as we pressurise and depressurise it in cycles, we will naturally fracture the rock mass. So we need to make sure we deal with the complexities that creates, and then that then essentially transfers the load out into the undisturbed rock zone. H2 loss is one of the biggest technical challenges. The molecule is tiny. Containing it is very difficult, so even steel itself can't fully contain hydrogen. So we need to have a look at the cyclic loading as well and how that interacts with the permeability of the containment material, H2 embrittlement. Steel suffers widely from that, and so hence we're looking at polymers and other things that can contain it. Also the cyclic nature, so low cycle fatigue, and structural deformation. So it wouldn't take much. A small crack in the tunnel containment system would end up with a large loss in hydrogen. So we need to consider the structural movements and the ground structure interaction movements, using things like the in situ stresses and the stiffness of the ground as key inputs. So it's a very, very complex system, and we've done some analysis, etc., on this at the moment, and we're now looking to move into a testing stage, which is again amazing to be here, in this facility. This is a very heavy slide. I won't go through it in all, but let's just focus on the circle. The gas membrane, so we're trying to contain hydrogen, and the membrane itself, whether it be steel or polymer, needs to be flexible for those movements to be accommodated and not crack. It needs to be water resistant, as someone mentioned earlier on. There's external groundwater and potentially water internally. It needs to be impermeable enough to accept the losses. and durable, obviously, over the design life of the structure. So hydrogen is not inert to all materials, so we need to look at the materials that we're using and how hydrogen interacts with those over time and in the cyclical nature. So having looked at all those inputs into the system, it's a very complex system. Before we are able to pressurize underground storage complexes with hydrogen using a new concept, we need to go through a technological qualification process. Just on the left here, it's all the issues that we need to validate before we get a patent or verify to the authorities that it's safe to store hydrogen. So we need to claim the solution is fit for intended use and essentially show compliance with relevant codes and standards, if any. One of the key challenges is that there are none, really, not in Australia anyway, where we're looking to do this work, and substantiate, if not, then substantiate the qualification of a new technology through an established process. So we've been working together with Fortescue and other companies that do independent certification to look at that. And just some more schematics, this is again from the paper from Johansson, is just looking at when we pressurize the tunnel, how that affects the surrounding rock mass, but not only from a structural perspective, but also leak, if there is an event of leakage, etc., what that means, So we have to cater for the best case, but we also have to cater for the worst case. Again, a very, very heavy slide. Unfortunately, I'm a consultant and I love this sort of stuff, so you're going to have to sit through this for a minute, if that's okay. So what we did is we developed an in-tunnel pressure analysis program that calculates over different geologies and different range of conditions whether the solution would be feasible at different scales. And again, it's a lot of inputs that need to go into this. We need to understand the rock overburden, the strength, the stiffness, properties of the lining, both structurally and from a materials perspective, the concrete properties and the liner properties. And from all the analysis where we get to is outputs of global rock mass deformation, rock mass failure extents, and induced stresses in the rock mass and how that causes cracking and fracturing. And looking at lining displacements themselves, is the amount of movement that we expect, is that going to crack the containment lining itself? And then we get to the decision phase, is the system feasible for the ground conditions that we're in? It's not going to be suitable everywhere. Fortescue would like us to say, yes, we can do it anywhere, somewhere in 20 metres under Amsterdam, for instance, but unfortunately we can't. So we get to a decision stage, is the location suitable for the application that they're asking? So that's where we're at, and what are the next steps? So we've got a plan, and the stage one is now that having produced the reference design is to do some lab trials on the material itself from a permeability and a structural perspective. So understand it at a small scale in the lab, how the materials react. Scale trials on the system concept. So you saw the slide earlier on of the 7 components in the system, try to understand that. Numerical modelling to validate all this, and then feed that back into a scale, and have that feedback loop of modelling and testing on site, after which we would get the technological certification and advance to a full-scale pilot project, hopefully at Hagerbach, but we'll talk about that in topic 3. So thank you very much.
Thank you very much. Thank you indeed, Ahmed. Next speaker is then Reinhold. Is it Christian?
Just click one.
It is Matthias. Sorry. Please, Matthias.
Okay, so I would like to talk about some engineering considerations when we are creating underground hydrogen storage. Being the 6th speaker, basically most things I wanted to say are said already, which gives me the opportunity to focus on most important things. Normet being material and machine supplier, we are doing things, or we are providing the means to do things in also developing those materials. So why do we need hydrogen storage? I think we went through that a number of times. We want to make that safe, and then we need to consider all the different aspects, geotechnical, but also obviously the material aspects. The market, who needs the hydrogen, we went through that. Maybe just heavy industry, as we can see here from pictures in Germany and Belgium. Those above storage tanks are most likely not hydrogen. I would say they are natural gas, but the concept is the same. Transportation is a big issue, even though we are probably not 100% aligned in our opinions. But Europe has made the decision to electrify transportation and personal cars especially. But on the back of that, actually, with the fuel cells, hydrogen is coming back into the game. And then also large scales, obviously, ship fueling, train fueling stations, and national protected stockpiles as a secure energy source. And of course, also civil defense organizations have interested in storing hydrogen. So that's a few examples of how an underground hydrogen storage could be built. On the left, a tunnel excavated and mechanized tunneling. That could also be a deep shaft. Doesn't matter which way we are going. And then on the right, rock caverns and tunnels lined with sprayed concrete. And then obviously the alternative, large above ground storage facilities. So which way do we need to go? I don't think we can answer that question because there's multiple aspects, like in engineering, always to be considered. And there might be justification for both solutions. But what I would like to emphasize is actually that the challenges and the tasks we need to work on are very similar. There's a wide overlapping area. First of all, we need to define our and construct our confinement structure, and we need to have the gas tightness concept, whether we are above or underground. And then the question is there whether it's a long-term storage or a daily filling and emptying, which then obviously defines load cases, forces and stresses on our structure, which then lead into pressure changes, deformations, fatigue behavior, creep, and then obviously cracks in most brittle materials. And then the durability aspect of all that, the hydrogen embrittlement on steel, but also other materials, and also other degradation effects of hydrogen. And then obviously operational safety, gas monitoring, etc., and maintenance schedules. So now, as the scientific and engineering community, there's a number of aspects we can work with when we want to store hydrogen, or when we want to store gases in general. So if we look at this equation, which may look familiar to most of us, we want to store a large amount of gas, obviously. Then we can work with the pressure, we can work with the volume, or we can work with the temperature. And we have heard actually about all those aspects already today. What creates us the most pain is actually the pressure. So if you have large pressure changes, that causes movement and fatigue. And hence, it could be interesting, maybe we need to increase our storage volume and have not those massive pressure changes. But those are numbers, or those are parameters we can work with. We can then also work with technology or the containment structure. Are we going very deep or are we going shallow? Are we using deep shafts, large caverns, long or short, large or small diameter tunnels? So we can work with all those parameters. We can even think about salt caverns or depleted oil and gas fields or aquifers. And then we can work with our gas tightness concept, and actually quite refreshing and interesting this morning so far. There are different ways of containing gas, and if we look into a natural gas reservoir, there is actually no steel liner, there is also no polymeric liner, there's clay or limestone or probably shale. We could also think about using materials like that. And then, as mentioned a number of times, we can also think about which gas we are going to store. Hydrogen with very small molecules, obviously, is very hard to store. The energy density is not great, so we probably could go back to our methane, similar to natural gas, or in some cases, ammonia, for example. So, R&D topics resulting from all that. Obviously, there's geotechnical and rock aspects. There's the lining aspect to have the mechanical structure. And then there's gas tightness aspects that we need to look at and research on. At the end, our topic mainly is or was in the past steel versus a polymer liner. And since we are not a steel producer, we are producing chemicals. We are particularly interested in polymeric liners, which can have advantages in our opinion, and we are about to prove that. And here's just some, I'm not sure whether I can start that. On the right-hand side, we can see no, I can't. We can see just an elongation testing on a sprayed membrane, and the top one is a crack bridging. Maybe we can start it from the computer. Would actually be nice to see it.
It's working.
Yeah. So the elongation, it doesn't look very spectacular, but if you think of a design life of 20 years or 50 years, and the daily filling and emptying, that's probably 20,000 load cycles. And well, that is part of the research. We need to find a material that can do that, or we need to find a containment structure that doesn't have that issue that much. And then on the top, you can see actually the crack bridging behavior here where the decoloring happens. Obviously, that is a non-reversible damage of the membrane. But a crack like that would be very unusual as well. Then R&D steps, desktop studies done. I'm referring here actually to this, basically to this FFI project that Anmol also mentioned earlier. Desktop studies, then small scale and material tests have been done. We are still working on that. And now the next step would be a prototype, probably a smaller or even larger pilot project, and then that costs money and we need funding. That's why we are talking here. And then one example of actually that research can be funded is this FFI project, which results actually in at the bottom here. So we have defined the membrane requirements. We have tested containment successfully, and most of the load cases are actually defined in that project as well. That's just a few pictures of underground spaces. On the left side, a sprayed membrane is being applied in two coats, two colors for quality assurance reasons. That's what it could look like. More membrane testing, or membrane spraying, I should say, in full scale on panels here. That's a few pictures from road tunnels in Australia, which are actually also quite large caverns in sandstone here. So that could be our gas membrane. In that case, it is a waterproof membrane, and then it also is sandwiched in here, which wouldn't be necessary for hydrogen storage necessarily. And just to sum up, that's the steps of material development we are in, or we are undergoing, defining the parameters and the structure, and then developing the right materials and testing the materials in their gas tightness behavior, but also fatigue behavior, which is probably the higher emphasis. We have membranes that are very tight to hydrogen, but it's the longevity of the game. And then the next step is full-scale spray trials. That might be robotically or manually, and next step then would be the proof of concept in a pilot project that I think most of us would like to do here at some point. And with that, I'm at the end of my presentation. Thank you.
Next speaker is then Pascal, please.
Yeah, so I think, so I will not repeat what my colleagues have said, because most of the topics that we are reaching are similar to the ones which have been highlighted by either the previous one or Normed. So, but maybe I will add one challenge which will be on the construction process itself. So it's more on constructability also, because this is one part. There is the part of calculation, there is the part on the material, but there is also the part on constructability. So what the concept that we are looking at is something similar to what has been proven for natural gas in Skalen in Sweden more than 20 years ago. It was 1980 something, if I'm not wrong. So it's a kind of vertical silo with a sandwich of different materials and with the management of the water with some drainage and some possibility to pump out the water if we have to decrease the pressure inside and not to collapse the liner, which will ensure the tightness of the silo. So here more some illustration on the way we think it will be constructed. So for the excavation, it will be a drill and blast in very competent rock. So starting from the upper cupola and then going down with the silo to be first pre-cut to avoid some damaged rock and overbreaks around with different access level, and then maybe a raise boring in the middle, then to enlarge the silo, by going down, and then excavating the bottom part. I think the excavation itself is not the main challenge. The challenge will be on the quality of the excavation to avoid the rock mass deterioration around the silo. But excavating the silo with drill and blast, it's quite flexible, so this one will not be the biggest challenge. Then the challenge might be on the steel liner installation. But the steel liner has to be installed. What we think will be a viable way is to install it from the bottom up, so it's with a jack-up system. So after the installation of the liner, at the bottom and concreting around the liner, it will be filled with water to counterbalance the pressure. And then we will install the liner step by step with the jack-up system up to the top. So you can see here the different steps of the liner installation, layer by layer, ring by ring, up to the top. So this is one of the challenges, it's to install the liner within the required tolerances, for example. This is one of the challenge. And then the size of the silo will have to be also compatible with something which is doable for the jack-up system. And then the second challenge will be the concreting. Because this one, when we are thinking about the silo 25 to 40 meters diameter, it means that you have to distribute the concrete all around in a very specific way to avoid the deformation of the steel liner. You have to fill it with the water at the same time to counterbalance the pressure. And so this is one of the biggest challenge. will have to be also verified on in situ test to ensure that it will be doable. So this will add to the challenges that I've presented already the previous panel. This is what we are thinking about. The pressure, the storage pressure will be between 200 to be economically viable. It has to be between 200 to 250 bars, something like that. So with the different diameters, you have a table here with different diameters that we are thinking about, 24, 38, or 40 meters. 50 meters will be a big challenge because this one, it has to be supported also during the installation. It has to be self-supported with the rock bolts and shotcrete. So this might be a challenge depending on the rock quality. But the most probable solution will be something like 40 meters diameter, 80 meters height. So at 200 bars, you can store 1,000 tons. This is the equilibrium that we are thinking about between the size and the volume to be stored for economical reasons. This is exactly the same as presented by Mr. Bedi for the sandwich. So you have the rock mass, you have a drainage system starting from the top to the bottom to the internal part. So the rock mass, a drainage system, a concrete sealing part in between the steel liner and the silo. And in between the steel liner and the concrete, there will be a kind of sliding layer. So the sliding layer will allow the steel liner to move independently. So for sure, when you are applying the 200 bars pressure inside, there will be an increase of the diameter by a few centimeters, up to 10 centimeters, saying something like that. So it means that there will be cracks in the concrete. You cannot avoid the cracks. The steel liner will go to the plastification. So depending on the cycles also, this is the importance also in the design, the cycling of this liner and the resistance of this under these different cycles. So the sliding layer will allow the steel liner to move independently and then to cover the cracks. So the distribution of the cracks will be important. It will be partly governed by the rebars which will be installed to distribute uniformly the cracks among the concrete. But the sliding layer will help also covering these different cracks. So you are talking about 10 millimeters cracks. We are hoping that the cracks will be more close to 2 millimeters or something like that. We are hoping it will be easier. So all these are technical changes which have to be tested. So So the different parts will have to be tested. I think it will be on my next one. There is a second challenge, a third challenge, so constructability, the challenge on the different materials, but there is also a challenge which has been also highlighted, which are the regulations to be applied. Because right now there is no clear, at least in Europe, I don't know for other countries, but I think around the world it's something new also. There are no regulations to be followed for this different storage, H2 storage. So for example, which type of, will it be considered as a pressurized vessel? For example, in France, pressurized vessels, there is a clear need of regular inspection, so it has to be inspected from internal part every 5 or 10 years, depending on the pressure, and then it has to be tested every 10 years. So will it be the same? Because the silos that we are thinking about with 40 meters diameter, 80 meter high, it will be definitively closed without possibility to re-enter after 10 years. So this one we have to deal with authorities to find new regulations, but we have to demonstrate that it will be tight and that it will be still safe after 20, 30 years, because we are not constructing this for only 10 years. Then there is the challenge of the risk of leak. What will be the acceptable leak, how to detect a leak, and how to ensure the authorities that the leak will be contained within the collecting. Here we are thinking about the drainage system, which will be full of water, of natural groundwater, and which will allow collecting the hydrogen to flare on the top or something to ensure to verify the amount of the leak. Then, for example, there is another challenge which we are discussing with authorities, whether there will be a need of subsurface safety valve. In natural gas or in gas that, for example, we are operating a lot of salt caverns with gas, there is a mandatory safety valve installed at the bottom of the shaft. It's why, because if there is anything happening, you close the valve as close as possible to the reservoir, and then you have only one part of the gas which will be leaked in the shaft. Okay, but here, due to the inflammability of the hydrogen, even for the small part, we are thinking about something like 200 meters of shaft connecting the surface to the reservoir. So this one, even with the amount of hydrogen which will be within this part of the 200, you achieve the maximum dangerosity of the flame above ground. So whether there will be a need of the bottom safety valve or not, this is also one question that we have to deal with authorities. So what we are contemplating now for the development of this is different steps, the same as highlighted by my colleagues. So first is the test on individual materials, the sliding layer, the steel liner, the concrete and the different parts. Then it will be a testing on something with assembled materials. So it will be a sandwich beam, for example, or a small can. We are also thinking of maybe a small can, 1 meter diameter, 2-3 meters high, something to test what will be the behavior of all the materials within this. Then it will be, there will be also consideration on constructability, which we are discussing also. Then there will be a construction of a pilot, kind of pilot. So the first, the assembled material will be a kind of proof of concept. But then there will be a pilot, 1/3 or 1/2 of the full-scale capacity. And then operation of this one with strict monitoring around to check whether the actual behavior under operation is similar to what is expected. And then the full-scale project. So here you have in red the different steps. So the first one is few months, few millions. The other ones also for the proof of concept. But then we are going to the pilot scale. Whatever will be the size, whether it will be 20 meters diameter, 40 meters high, or 150 tons capacity or something like that, you will need 200 to 300 millions of euros to store this, to construct this. And then for the full scale, it's 5 to 8 years, and it will be for 4,000 tons, for example, it will be close to 1 billion euros. So all this, for the first two steps, it can be funded by different subsidiaries from authorities, but then when we come to the pilot, even for small capacity, there will be the problem will be also to find all the funds. I think it's the same as highlighted by Normet. It's how to find these millions for this. So this will be a challenge. So for us, the development of this underground in lined rock caverns will be whenever there will be no possibility for other storage for large capacity. For salt caverns is the most efficient, costly. So whenever there will be no salt possibilities, it will be interested. The technique has still to be finalized, and the cost versus the other possibilities has also to be in line, because, for example, for the H2 pipeline, is for 1 kilometer is 1 to 2 millions. So if you have facilities, if you have salt possibilities 50 kilometers away from the need, it might be more interesting to have salt storage facilities rather than lined rock caverns with a pipeline. So this one has to be. And I want also to mention here other possibilities which are already proven, the proof of concept, and even some small-scale projects have been completed. This one is from concurrent, it's not from us, but I want to mention because it's quite interesting to have maybe the possibility to have supplementary possibilities on the same site. Here, for example, is the system Delphi by Vallourec. Vallourec is constructing some pipes. Here, the concept is to excavate a shaft up to 100 meters deep, 10 meters diameter, and then within the shaft, they suspend some pipes. Okay, the storage capacity of this, they are mentioning 1 to 100 tons. It's closer to 1 to maximum 50 tons, something like that. So it's for small capacity, but the footprint is a bit different from the above ground storage. There is another one, which is an Australian company. It's Ardent. Ardent, they are working on the concept of blind boring shaft and then installing a liner inside and then concreting. So it's nearly the same concept as the line rock caverns, but within shafts which will be 5 meters diameter. So they are thinking also, here it's a bit optimistic, 100 to 150. They are more thinking about around 50 tons, something like that. So these other systems exist and can be a supplement. If a client wants quickly some storage capacity, we can first have this kind of small storage, and at the same time excavating the larger storage. It would be an interesting idea to have this in supplement. And here is just to illustrate the different cost versus the capacity. So it's something which has already been presented. But so for large, very large capacity, the most cost-effective is salt cavern, but the line rock cavern can be also interesting for very large capacities. I think that's it. Yeah.
Thank you, Pascal. Thank you very much. Okay, Christian, you are the last speaker of this session. I think we are probably going a little bit overdue on time, but I hope that's okay.
Okay. What we are working with in Horisont Energy is two projects at the moment. One is a large world-scale ammonia plant in northern part of Norway. It's when you see Glomfjord on the map there, we are on the very top of Norway in Hammerfest, and where we are going to build, construct and operate a plant, ammonia plant with 3,000 tons per day of ammonia, or 1 million tons of ammonia per year. And if you convert that into hydrogen, the amount of hydrogen contained in that ammonia is basically, what do I say, divided by 5, so then you get 200,000 tons of hydrogen would be per year produced into that plant. So 200,000 tons of hydrogen is the equivalent. What we are going to do into that plant is to store it into a unlined rock cavern storage. We are now looking into the more details on that, and where we will be storing it in an unlined rock cavern. Along with that rock cavern storage for ammonia, we are also planning an LPG storage, because the gas source, this ammonia plant is going to be a blue ammonia plant. It will be based upon natural gas from the Snøhvit or Snow White fields in northern part of Norway at the Barents Sea. We are going to use that gas. Given some instability in the supply, we are also looking into safeguarding ourselves by having an LPG storage, so a rock cavern LPG storage on the same site, and where those two storages is going to be located side by side to utilize the cryogenic elements of this one. So having the two storages located some 50 to 100 meters apart would benefit from the cooling perspective, because we are going to commission, when you are commissioning these two storages, you need to cool down, and then of course in the long run you would probably reduce the energy consumption also by having those storages fairly close to each other. The LPG storage will be basically 40 minus, and the ammonia is minus 33. So this is the concept which we are currently working on. As Øyvind said, we are working with a carbon capture project where we are going to operate a terminal for CO2 captured elsewhere, where it's going to be shipped into the terminal. We are going to have a intermediate storage, and where we are going to have a pipeline from that intermediate storage out to a field in the North Sea, or multiple fields in the North Sea, where the CO2 is going to be sequestrated. The transportation of that CO2 will be at either minus, say, around 6 bar pressure and minus 55 centigrades, where it's liquefied, or say 15, 16 bar pressure and minus 27 to 30 centigrades. The facility which we are going to operate there will have both possibility to import both pressure levels. So that's one thing. And in this context, we have been, Øyvind have been helping us looking into the possibility of using a rock cavern storage for the CO2. So of course, looking into all the capture and sequestration projects which are globally, if we could solve the issue of intermediate storage being on the emitter end or on the sequestration end, that would help a lot. So my hope is that some of you or someone in the near future would be able to come up with a viable prospect of doing CO2 storage, underground storage. Of course, from a pressure point of view, it's not a big issue from containment, and from a leakage point of view, as long as you have, as you keep it deep enough, or if you freeze it, then you may be, or having it liquefied at these temperatures, you will create a frost zone, and then given that the authorities and the permit givers, they accept the solution which we are talking about here, that could be a very good way of doing things. The only issue which I currently see is pumping and using deep well pumps when you're having the pressure. That could be a possible issue. So having somewhere where you can have dry pumps located in a rock cavern adjacent to the storage cavern itself, I think those are some of the ideas to play around with. I've been working with ammonia and hydrogen projects since my infancy almost. And this project, I was working in the Glomfjord plant from 77 until the early 80s. So I was part of starting this project back in 81, and where we had an early rock cavern storage where we were storing pressurized ammonia into a rock cavern, where we had a lot of issues with, not in Glomfjord, but in Herøya in Norway, where we had a lot of issues of water ingress. And then creating a lot of ammonia water and trying to get rid of that, you have to strip it and all these things. So eventually that one was abandoned and they put on an above ground storage. In Glomfjord, we had two sources of ammonia. One was the ammonia produced at site. The other one was from a coke plant where we're producing pressurized ammonia. Then when that coke plant stopped, then we did not get pressurized ammonia anymore, so we got liquefied ammonia. Then we were looking for how to store that liquefied ammonia. And seeing that a rock cavern storage would be a much cheaper alternative than an above ground storage, we opted for that, and the plant or the storage was designed, it was completed in '86. Main rock type was gneissic granite. The storage volume is 60,000 cubic meter. The width, height, and length was 16 meter for the main tunnel, and some cross tunnels 10 meter width, 20 meter height, and the total length is around 170 meter. The temperature between minus 28 and 33 centigrades. The pressure between 0.1 and 0.13 megapascal, max 0.2. This cavern serves as a buffer storage into the ammonia, which is imported by ships into Glomfjord. And the typical ship delivery consists of 10,000 to 20,000 tons of liquid ammonia. And the annual throughput on the storage is about 80,000 tons. The ammonia is pumped from the storage at a rate about 70,000 tons per month, but about 65% of this is immediately returned. So there's a ring pipe or a ring cycle where the consumers are pumping or consuming ammonia from. So about 540 tons of ammonia is returned from the fertilizer plant as gaseous ammonia, which is then liquefied. And the temperature in the storage is held constantly by condensing ammonia gas. So you have a boil-off from the storage, which is condensed by a compressor and a liquefaction system. And the installation was with two compressors, each with 300 kilowatt capacity, those two compressors. This is the layout. In those days when we started, we were very uncertain about what the configuration should be, but a donut shape was considered being a good shape, and then having a rock core in the middle who could take the pressure. So there was those two main tunnels and these crossovers. So at the end, it ended up with a hexagonal shape. And then you have the access tunnel, and then you had two access to and you were driving two tunnels in parallel, and so you put in two plugs, and then the Norwegian requirements is that you fill up with 20-meter water column above the maximum pressure you have. So the elevation of the tunnel was that the bottom part was around minus 75 meter, and the roof at minus 50 some meter. With the access tunnel and the plugs here. And then to safeguard that there would be no leakages, there was also put in a water curtain tunnel at the around 21 meter level with approximately 35 meter long boreholes to the side to create the water curtain. When you did the checking of the rock quality there, we drilled down to minus 125 meter, and there were only two small crack zones into this one in total. So the homogeneity of that rock is extremely good, that's to be said. The experience is that this rock cavern has been successfully operated since the startup in 1986. The only issue you had was during commissioning. The main cavern was cooled down to minus 22 centigrades by air, and then it was filled up with ammonia, approximately 5,000 tons of ammonia. When you started filling of the ammonia, a couple of days after putting the ammonia in, you saw that the temperature did not sink. And we realized that there was a leakage into the tunnel. And you could see that the leakage came from the access tunnel because the water volume or the water level in the tunnel was sinking. And then the commissioning procedure was abandoned, the tunnel was emptied, and there was put in 2 new concrete plugs into the access tunnel further up. And all the ammonia water, which was in the bottom of the storage, was pumped out. And so the storage was completely emptied for all the ammonia water, which was distilled and taken away. And then the tunnel was commissioned back again. And then it has been virtually done nothing with it. It has been operated safely for those years since 1986. The current boil-off is extremely low. And those 300 kilowatt compressors are only running partly every now and then. During winter time and summertime, it's just a couple of hours per day which they are running. So it indicates that the frost zone around the storage is there, and there is no ingress of heat from the surroundings. So the only heat which is coming there is from the pumping of ammonia. So this shows the benefits of having a rock cavern storage for ammonia, I think.
Thank you, Christian. Thanks a lot to all the speakers. We are a little bit over time, but I think it's also not very nice to intervene and interrupt when people have a lot of interesting and important things to say. If you allow me to just draw one single line between what we have heard, I think Michael is smiling because all of these people are actually crying out for some place to do testing. That's my conclusive thing from what I've heard. It's interesting well, when we go back to the 2 guys from Australia, down under, I was thinking, in Australia, there must be so many deep mines which have been abandoned because there is no more to take out. Have you ever been thinking or considering to sort of utilize any of these mines for this kind of storage?
Yeah, interestingly, Fortescue is a mining company. So they have a lot of mines. The problem is the very, very remote locations and infrastructure to set up pilot plants, etc. And the infrastructure just doesn't exist. And also, the regulatory bodies in Australia are a lot stricter than here, for instance. So to get permission to do it is also very, very difficult. So that's the current challenge of not being able to use their mines as trial locations.
Okay, yeah.
Maybe the other point is the design life of a mine. I mean, all the rock support systems are designed to last 15 years, 25 years. So actually, we could probably think about a block cave mine before the surface collapses. But I don't know how you stop the self-mining.
But for a testing facility, I mean, to create a safe room with some rock support and things like that is peanuts with respect to whatever is coming later on with respect to, making a full-scale thing. So
it should be possible, yeah.
Yeah. The reason why is that I know that somewhere else there are people looking at the possibility of utilizing abandoned mines for testing facilities. Maybe also for permanent use later on, but at least in the beginning as testing facilities. I was waiting for you, Reynold. You talked about, as also Anmel did, about polymers. And I was waiting and waiting. When will he tell us what kind of polymers he's actually considering? And late into the presentation, you mentioned sprayable membranes, right?
Yes, yeah. So that is basically the concept, also from the constructability point of view. We are looking into sprayed membranes, and from the gas tightness, polyureas are very good, and butyl rubbers. But this is short-term containment, so as similar as with steel liners or other metal liners, the longevity is probably the issue.
To Pascal, I think it's interesting to see that Skallen is being brought forward again, because that was a big project back in the kind of 80s or 90s maybe. I've been looking out for, solid documentation from that project, but I haven't really found anything which is available for the greater public, so to speak. I know that the Norwegian company Statoil, which is today Equinor, was to some extent involved in that project, but it's very difficult to find documentation.
It is.
It is, yes, we confirm it. Thank you very much.
It is. No, we have been working with one person who have been involved since the beginning, who is retired now, is Jan Johansson.
Yep.
And but he is very reluctant to give more details information on this. So it's a bit difficult. This is why, but it's a pity because we are starting from scratch, or nearly from scratch, for some points which have already been developed. For example, the sliding layer has been tested and has been developed for this Skallen project, which could be a good idea to share. But okay, we have to start from scratch also for this, for example.
Because that was one of the comments I wrote down here, is that why on earth aren't we taking benefit from utilizing what is actually there? We do not need to invent the wheel once again. It's been a long time ago. I mean, there must be something that we can reuse and build upon to take the next steps forward.
Yeah, but it's okay. I understand also that there are some economics issues behind this. For example, in Sweden now they have also developed a new pilot project in hybrid for the steel factory. So
yes,
this one is in operation for 1 year already, and but there is no information also coming from this one. So they have some advanced technology, I could say, compared to what we have right now. But okay, we are starting several years back to the same process, and it will be
Sweden is sitting next to Norway on the geographical map. So we have been trying to approach hybrid, but it's very difficult to get any information from that project also. So
maybe at least you share the same language. Easier for you,
well,
but for us,
basically
or nearly the same language. You can understand each other.
There's a whole lot of things, but I can see that you guys are pretty much on the same line, more or less, with respect to how you try to or how you plan to develop your concept. And again, as I said, Michael, you must be smiling because they are all crying out for some place to do some safe and sound testing. The time scale that we see, Pascal, you mentioned 8-9 years or something. I don't think Reinhold or Amund said anything about the time scale. But we are probably something like 10 years into the future before we see this in operation, whilst ammonia is and has been.
It's already there.
Yeah.
And I think that's one of the elements which puzzles me a little bit, because seeing the volumes required of ammonia which is for 2050, the guesstimates are 500 million tons of ammonia. Today there are being produced around 180 million tons of grey ammonia. And then trying to produce clean ammonia in that range, you need a lot of intermediate storage. And then of course, seeing that this ammonia is going to be used for the marine propulsion, basically, and some for chemical purposes, fertilizers of course, but the main thing is for the ship transportation, and seeing the requirement for intermediate storage, and thinking about harbor of Rotterdam. If you have been there, you know how congested it is to put a large volume of above ground storage tanks for ammonia. Is going to be an issue. You have the same in Antwerp, you have the same in probably all large harbors, and where this is going to be one issue. If you can solve the problem by putting it underground in a safe manner, then of course one thing is that it's much cheaper, probably a factor of 3 to 4, and then it's much safer. So the safety distances and the precautions and all these things which you have to take when you store it above ground, of course that's a major benefit if you can store it underground. And it's proven.
Okay, we are 10 minutes overdue. Thank you very much. Thank you. Thank you, Aurora, for keeping us up here.